Okay, this is the test 2 review. This test 2 covers section 3.2, 3.3, 3.4, and 3.5. Because we ran out of time, section 3.6 will be covered on test 3. So here we go. Question 1, question 2, and question 3. And I believe question 4, yeah, all 4 of those questions are from section 3.2, polynomials and their graphs. So question 1, we are to sketch the graph of the function. Same directions as on question 2. The way I instructed to sketch the graph of a function, pretty much 3 steps. Step 1 was to find the zeros. Step 2 is the y-intercept, and step 3 was the end behavior. So for question 1, let's start with the zeros. This polynomial is already in factored form, so all we have to do is look at the factors to find the zeros. The zeros are x equals 1. That comes from this factor. X equals negative 1 comes from this factor. And x equals 2 comes from that factor. It's also important with the zeros to consider the multiplicity to determine whether the zeros or the x-intercepts cross through the x-axis or bounce off of the x-axis. To determine multiplicity, you consider the factor and the exponent that's applied to the factor. Each of these factors have an exponent of 1. That means their multiplicity is 1. Any factor that has an odd multiplicity produces an x-intercept that crosses. So all of these 3 x-intercepts, or zeros, cross through the x-axis. Okay, the y-intercept of any polynomial function, or any function for that matter, is found by letting x equal 0. So, if we place a 0 in for all of the x's in this polynomial, 0 minus 1 is negative 1, 0 plus 1 is positive 1, and 0 minus 2 is negative 2. If you multiply these 3 numbers together, you're going to get the point 0, comma 2 as a y-intercept. Now the end behavior is determined by the degree of the polynomial. If the polynomial is written in this form, factored form, one way to find the degree is to consider the number of zeros with their multiplicity. There's 3 zeros, and each of them have a multiplicity of 1. Add up all the multiplicities, and you get the number 3. So this is degree 3. So what that means in terms of end behavior is one side of the graph is pointing up, the other side of the graph is pointing down. Which side is which is determined by the leading coefficient. The leading coefficient here, out in front of the polynomial, is 1. 1's a positive number. So that means the right side is going up, and the left side is going down. And this would be the same end behavior of a degree 5, or a degree 7, or a degree 1. Any odd degree is going to have the same end behavior. So what needs to happen now, transferring this information onto the graph, we have x-intercepts of 1, negative 1, positive 2, and a y-intercept of 2, with end behavior, left side's going down, right side's going up. All 3 of the x-intercepts cross through. And the graph looks similar to this. Now, what you got to realize on the exam, if this were a multiple choice question, then you wouldn't actually be graphing this from scratch. You'd be choosing the correct graph from a choice of 4. So what you would want to look for is a graph that has the correct zeros, the correct y-intercept, and the correct end behavior. Question 2 is a lot like question 1. Start by finding the zeros and the multiplicity. starting furthest to the right, we have this factor, x minus 3. That's going to produce a 0 of x equals 3. Now, if you look carefully with this factor, it has an exponent of 2 attached to it, or applied to it, which means it has a multiplicity of 2. Any factor that has multiplicity that's even is going to produce a 0 that bounces. Okay. This factor x plus 2 is going to produce a 0 of x equals negative 2, and since it has an exponent of 1 applied to it, that's an odd number, so odd powers produce x-intercepts that cross. This factor right here, normally when students think of factor, they think of a term in a parenthesis, and that's normally the case, but x to the third power is also a factor, and if you think about what value of x turns this factor into 0, that value is 0. So x equals 0 is a 0, and if you look at the exponent that's applied to this factor, the exponent's odd, which means this one also crosses. Now the y-intercept, if you let all the x's equal 0, 0 here, 0 here, 0 here, you don't even need to worry about these because 0 to the third power is 0, and 0 times anything makes the whole thing turn into 0. So the y-intercept is 0, comma 0. Okay. The end behavior again, is determined by degree. When the polynomial is written in factored form, you need to add all the, one way to determine degree is adding the multiplicity of the factors. So a multiplicity of 3, multiplicity of 1, and a multiplicity of 2. If you add all those numbers up, you get degree 6. Since it's even degree, the end behavior is going in the same direction. They're both either going up and up or down and down. Since the leading coefficient here is 1, it's a positive number. Both sides are going up. Left side's going up. Right side's going up. So, thinking about a graph, we have an x-intercept of 3, an x-intercept of negative 2, and an x-intercept of 0. And that's also our y-intercept. And behavior, left side is up, right side is up. So, going from left to right here, trying to connect the pieces, the graph crosses through the x-axis at negative 2, right here. Okay. Now, when I instructed this during class time, I made it a point to test in between values here, like negative 1, just to see how far down this graph goes before it turns back up. Again, if this were a free response question on a test, that's something you'd want to do. If this were a multiple choice test question, it really wouldn't matter. Just to keep this short and say, alright, it turns back up at some point, crosses through at 0, okay, and then eventually it's going to have to come back down over here and bounce off the x-axis at 3. Now, again, graphing this by hand and producing your own graph, these might not be exactly accurate. What happens here is the graph has a few turning points where it kind of goes up and down, bounces, and comes up like this. Knowing where these go up and down isn't super critical right now. Okay. All that really you need to know is how to find the x-intercepts, how to determine whether it crosses or bounces like this one, what the end behavior is. Okay. Question 3, we still have to do the same things as in question 1 and 2. Before we do that, though, we have to write the polynomial in factored form to find the zeros. So, if you look at all three terms, the common factor in each of the terms is x, or in this case, negative x. If you factor out negative x, you're left with x squared plus 2x minus 5. Now this problem is slightly unusual in the fact that normally when you're left with a quadratic factor, you'll be able to write that as the product of two factors simply by using simple factoring techniques. It turns out that x squared plus 2x minus 5 doesn't factor. So that could mean one of two things. This quadratic factor produces two irrational zeros that we would have to get in the quadratic formula. So they still produce x-intercept, because irrational numbers are real numbers. They're just decimals. Or this quadratic factor produces complex zeros, or imaginary zeros, that don't actually turn out to be x-intercepts. Both of those cases we'd have to use the quadratic formula anyway. So x equals the opposite of b, plus or minus the square root of b squared minus 4 times a times c all over 2a minus 4 times 1 times negative 5 is 24. So this is going to produce real numbers because we're not taking the square root of a negative number, but they are going to be irrational zeros, meaning decimals, kind of unusual decimals. We're not going to get integer zeros like -2 and +3. So to figure out what the decimal values of these zeros are, you need to figure out what the value of this expression here is. So the plus and minus means you have to split this up into two problems. -2 plus the square root of 24 divided by 2, 1.45. And the other one, -2 minus the square root of 24 divided by -2 is 3.45. So those are the zeros, and they each have a multiplicity of 1. Now the y-intercept, well actually we forgot 1 0, we only found 2. There's supposed to be 3 zeros because this is a degree 3 polynomial. We found 2 zeros here. The other 0 comes from this factor right here. The only number or value for x that would turn that factor into 0 is 0. So x equals 0 combined with these other two. Those are all 3 of the zeros. So now the y-intercept, if you let all the x's equal 0 in this polynomial, you would get 0 minus 0 plus 0, which is 0. So the y-intercept is 0 times 0. The degree, or the end behavior, since this is degree 3, and the leading, well in this case the leading coefficient now is negative. So that means the end behavior switches. The left side is going up and the right side is going down. So for this graph, a little teeny one over here, this graph, we have a 0 at 0. And you know what? This isn't looking right. Divided by -2. That should be a +2. So that should really be a -3.45. Yeah, 1.45. And -3.45. So all 3 is zeros. There's a y-intercept right there. The end behavior is left side's going up, right side's going down. So all 3 of these zeros have multiplicity of 1, which means they all cross through the x-axis. Crosses through. At some point, again, if you were doing this by hand, you'd want to check one of these in between values to see exactly how well this graph goes before it turns back up. Same thing here, you just want to find out when x equals 1 exactly how high the graph is. Okay. Question 4, determine end behavior. This is another degree 3. And since the leading coefficient is positive, we know the right side's going up and the left side's going down. But the way that you describe this, or notate this, is using x's and y's. So considering this piece of the graph here, the right side, if you think about points on the graph and traveling from left to right, x values are getting bigger and bigger and bigger, which means they're approaching infinity. And the y values are also getting bigger, which means y is approaching infinity. Similarly, on the left side of this graph, if you think about the points on the graph, okay, as you're traveling now in this direction, the x values are getting smaller and the y values are getting smaller, or they're getting more negative. So x is getting more negative, which means it's approaching negative infinity, and y is getting more negative, which means it's approaching negative infinity. So all 4 of those questions, question 1 through 4, section 3.2. Question 5, find the quotient and remainder using long division. This is from section 3.3. Okay. Now it says specifically to use long division, and even if we had the choice between long division and synthetic division, we'd have to use long division because of the divisor. It has an exponent of 2, any exponent greater than 1, and you've got to use long division. So one thing that you want to look out for is missing terms in the dividend up here, or in the numerator, and it doesn't appear that there's a missing term, but it actually is. There's no constant at the end of the polynomial. Usually there's a a plus 5 or minus 10 or something out here. So you have to have a 0 in there to take the place of the constant. So 6x to the third plus 12x squared plus 13x plus 0. And there's also a missing term here in the divisor. There's no middle term, so we have to have a 0x. Okay. Now to consider first term and first term. 3x squared divided into 6x cubed. Well, 3 goes into 6 twice. Okay. And x squared into x cubed gives you an extra x left over. So 2x multiplied by 3x squared is 6x cubed. You also have to multiply the 2x throughout this divisor polynomial. So 2x times 0x is 0x squared, and 2x times 5 is 10x. The phrase I like to use is draw the line, change the signs, change all the signs. First terms cancel. 12x squared minus 0x squared is 12x squared. 13x plus negative 10x is 3x. And we drop down the next term, start again. 12x squared into, 3x squared into 12x squared is 4 times. 4 times 3x squared is 12x squared. 4 times 0x is 0x, and 4 times 5 is 20. Draw the line, change all the signs. First terms cancel. 3x plus negative 0x is 3x. 0 minus 20 is negative 20. So this is a quotient, and this is the remainder. Question 6 is to find the quotient and remainder using synthetic division. So this is done by an upside down long division bar, and you have to check the dividend up here in the numerator to make sure there aren't any missing terms, and there aren't. And then we're synthetically dividing by the 0 of the denominator, which in this case is 9. Okay, and start the synthetic division algorithm here, drop down to 1, multiply numbers on the outside, 9 times 1 is 9, add the numbers on the inside, 9 plus negative 7 is 2, 9 times 2 is 18, 26 plus 18, it's going to be 44. It's never a bad idea though on these tests to check your math. So 26 plus 18, 44, 9 times 44 is 396 minus 386 is 10. 9 times 10 is 90. 90 plus negative 87 is 3. So that's for the quotient and the remainder. This is the remainder. It wouldn't be correct just to circle these numbers to say that this is the quotient. Remember, these are the coefficients of the terms of the quotient. If we started with an x to the 4th and divided by an x to the 1 polynomial, that means we're left with an x to the 3rd polynomial. So x to the 3rd plus 2x squared plus 44x plus 10. That's our quotient. Okay, question 7 is also from section 3.3. This first part weren't here, and all it said was to evaluate p of 3 for this polynomial. You just replace all the x's with 3's and be done with it. And that's okay to do just to see what the answer is, but to get credit for this problem, you have to show that you use synthetic division and the remainder theorem. Now, the remainder theorem, well, let's first start with synthetic division here. 1, 4, 8, and 9. And when we're using the remainder theorem to evaluate a polynomial, you actually use this value here. The remainder theorem states that whatever value you get as the remainder, that's what you would get if you plug this number into the polynomial. So, let's see what we get. Three times 29, let's see, it's going to be 87, better check that. Okay. 9 plus 87 is 96, so the polynomial evaluated when x is 3 is equal to 96. Okay, and just fair warning, if this is a free response test question, and all I see is this without any of the synthetic division and remainder theorem shown, you won't get credit for the problem. Okay, question 8. Find a polynomial that has these 3 zeros, and it's got to be degree 3. So if you already have the zeros, your next step is to form the factors that would have produced those zeros. So if the 0 is x equals 9, then the factor itself is x minus 9. And similarly, if the 0 is x equals negative 9, then the factor is x plus 9. And if x equals 6, the factor is x minus 6. And this is polynomial p of x. Now your next task is to multiply these 3 parentheses together. So if you take the first two here, x minus 9 has x plus 9, and multiply them together, then you get x squared plus 9x minus 9x minus 81, which simplifies to x squared minus 81. And that needs to be multiplied with the x minus 6. Now x squared times x is x cubed. X squared times negative 6 is negative 6x squared. Negative 81 times x is negative 81x. And let's see, negative 6 times negative 81 is going to be positive. Let's see, 6 times 80, 486. Let's just double check this. 81 times 6 is 486. And that's the polynomial p of x. Okay, question number 9. is from section 3.4. It's only asking you to do one very specific thing, just give all the possible rational zeros. Essentially what it's asking you to do is give P over Q list, and that's it. You don't have to test them to see which ones are zeros, because it says don't check. Just give the list of possible rational zeros using the rational zeros in. So the values of P come from the constant. The values of Q come from the leading coefficient. So if P are the factors of 8, that means P is equal to plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. The values of Q, since Q is equal to 1, are just plus or minus 1. So to take all the values of P separately and divide them by the values of Q, dividing by Q, since Q is 1, isn't going to change any of the values of P. So P divided by Q, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. And that's all it was asking you to do, is give a list of the possible zeros. There they are. Question 10, also from section 3.4, is asking you, from the graph, determine which of the possible rational zeros actually turn out to be zeros. So first it's saying, what are the possible rational zeros? So you've got to do the same thing that we did up here in question 9. So we need P, we need Q. P are the factors of the constant, which is plus or minus 1. And Q are the factors of the leading coefficient, which in this case are plus or minus 1, plus or minus 5. So then P divided by Q, if we have 1 divided by 1, that's just 1. But then if we have 1 divided by 5, that's 1/5. So these are the list of possible rational zeros right here. It says use the graph to determine which of these actually turn out to be actual zeros. And remember, zeros are the same as x-intercepts. So we have an x-intercept here, here, and here. Do those match up with any of the values from our list of possible rational zeros? And obviously we have 1 and negative 1. And we have the one here. Now 1/5, about 0.2. So it's about a quarter of the way. And obviously it's a positive one because it's on the right side of 0. That looks like it is about a quarter of the way between 0 and 1. So according to the graph, we checked from our list of, so we didn't even have to do synthetic division to prove any of this. And those actually are the zeros. Now it doesn't ask you to do this, but if you wanted to be sure, you could do synthetic division on these to make sure you get a remainder of 0. I'll show you here. Subtract on the 5 and multiply. We get a remainder of 0, so 1 works, and it would be the same for the rest of the other 2 zeros. Okay, next question. Question 11, and this, the next 7 or 8 questions pretty much are all the same type of thing. Find the zeros. Very important skill coming out of chapter 3 is to be able to find the zeros of the polynomial. It's pretty much the same process over and over again. It's just every polynomial is different and you get different zeros. This is a degree 4 polynomial, which means it's going to have 4 zeros. First step is to list the possible zeros. And that's your P over Q list. The values of P, remember, come from the constant 6, well in this case negative 6, so we got plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. The values of Q come from the leading coefficient, plus or minus 1. So 1 divided by 1, 2 divided by 1, 3 divided by 1, and 6 divided by 1. Plus or minus 2, plus or minus 3, plus or minus 1, 2, 3, and plus or minus 6. Those are our possibilities. Okay? Possible rational zeros. Now we just got to start testing. We're going to start with positive 1, see if that one works. And it may be that you have to go through a couple before you find any that work. So it's just something that you wouldn't want to rush through. Looks like we got luck in the first try. X equals 1, which means that x minus 1 is a factor. The other factor comes from these coefficients, x to the 3rd plus 6x squared plus 11x plus 6. Now we've only found 1 0, there's 3 to go. So we're going to go back to this list. The reason you have to refer back to the P over Q list is we have an x to the third reduced polynomial, and you can't use the quadratic formula on an x to the third polynomial. So I'm going to test negative 1. And now I'm going to test negative 1 on the reduced polynomial, 1, 6, 11, 6. And second try, we got lucky. X equals negative 1. So up here in this step, we had two factors, x minus 1 times this other factor. Now we've got an additional factor, so we have x minus 1, that came from this 0. We have x plus 1, that came from this 0. And then we have this reduced polynomial of x squared plus 5x plus 6. Now we do have a quadratic factor, so you have two choices. Either it factors into two more factors like that, or you have to use a quadratic formula to find the zeros. In this case, this quadratic factor factors into x plus 2 and x plus 3. So we have all four factors, x minus 1, x plus 1, x plus 2, and x plus 3, which means our zeros are x equals 1, x equals negative 1, x equals negative 2, and x equals negative 3. Okay, question number 12. Find all the zeros, and this time you got to use the zeros to sketch the graph of P. So, P over Q. Just to start speeding this up, you'd have to go through and list the values of P, then the values of Q, and divide them all to get P over Q. But it's just going to turn out to be for this one plus minus 1, plus or minus, oh boy, let's see, 80. We're going to have plus or minus 2. 3 doesn't go into 80. 4 goes into 80. 5 goes into 80. I don't believe 6 goes into 80. Or 7. 8 goes into 80. 5 goes into 80, I think 16 times. Yeah. 4 goes into 80 20 times. 2 goes into 80 40 times, and 1 goes into 80 times. So those are all the values, all the possible zeros, all the possible rational zeros of this polynomial. So we've got to go through and check them. So we'll start with 1 here. Looks like that one didn't work. We can try negative 1. Alright, that didn't work. This might take a while. Got a pretty good feeling here about positive 4. Because I knew what the answers were beforehand. But eventually you would have gotten there. So x equals 4. That also means x minus 4 is a factor, and these would be the coefficients of a reduced factor of x, or the reduced polynomial x squared minus x minus 20. And again, this is kind of nice. This quadratic factor here, x squared minus x minus 20, can be factored into x minus 5 times x plus 4. So the three zeros are x equals 4, negative 4, and 5. The boys, I want a graph. Let's see. I'm labeling these axes now is I'm going to label the x and y slightly different because we have a y-intercept of 80. So the y-intercept is 80. We have zeros of 4, -4, and 5. This is a degree 3 with a positive leading coefficient, which means the end behavior is left side is down, right side is up. All three of the factors have a multiplicity of 1. That's odd multiplicity, which means the zeros cross. So crosses through and comes up. And again, if this were a free response question, you'd have to plug in some of these values between -4 and -4 and 0 to find out exactly how high the graph is. It may turn out to go a little bit above the y-intercept and come back down. Crosses through 4, crosses through 5, matches up right about there. Okay, question 13, find the zeros. This one, values of p plus or minus 1, 2, and 4, but now the values of q are a little different. We have a leading coefficient of 9, so it's plus or minus 1, 3, and 9. So the values of p over q, you've got to divide all the values of p by all the values of q. So 1 over 1 is 1, 1 over 3 is 1/3, and 1 over 9 is 1/9. Now move over to 2, 2 over 1 is 2, 2 over 3 is 2/3, and 2 over 9 is 2/9. Then move over to 4, 4 over 1 is 4, 4 over 3 is 4/3, and 4 over 9 is 4/9. So those are our list of possible rational zeros. Maybe synthetic division to find the sum. And you would most likely start with 1 and -1 and then try all of the whole numbers. 1, -1, -2, 2. Just to save some time here, and because I know the answers are, I'm going to choose -4. So x equals -4 is a 0. That means that x plus 4 is the factor. The other factor comes from these coefficients, 9x squared minus 1. So we're at a slightly different situation here. This quadratic factor doesn't really factor using traditional factoring techniques. So you could use the quadratic formula, or you could recognize this as the difference of squares. This factors into 3x minus 1, 3x plus 1, if that's something that you can easily recognize. If not, one thing you could do, since this only has two terms, it has a squared term and then a constant term, you can set it equal to 0 and solve the equation. If you add 1 over and divide by 9, you're going to get x squared equals 1/9. If you square root both sides, then the square root of 1/9 is plus or minus 1/3. When you take the square root of a fraction, you square root the numerator and you square root the denominator, and don't forget the plus or minus sign. So we have our three zeros of x equals plus or minus 1/3 and x equals -4. Okay, question 14, more of the same, and again, p over q, since q is just 1, if you take all the factors of p and divide it by q, which is just 1, then essentially p over q list is just the p list, which is plus or minus 1, plus or minus 5. So, we try 1 here. This is not looking good. We try -1. Not looking good either. Try 5. Okay, this isn't looking good either. We could try -5, and hopefully -5 is working. There we go, first try. So if x equals -5, that means that x plus 5 is the factor. The reduced polynomial comes from these coefficients. That's going to give us x squared plus 6x minus 1. And shoot, this quadratic factor doesn't factor. And we can't use the same technique as we did over here because there are 3 terms in this. So, only choice is to use the quadratic formula. X equals the opposite of b, plus or minus the square root of b squared minus 4 times a times c all over 2a. (36) minus -4, that's going to be 40. And if we simplify this polynomial, the square root of 40, 40 is the same as 4 times 10, or the square root of 4 times 10, which means the 4 is going to come out as a 2. So it's -6 plus or minus 2 square roots of 10 all over 2. And if you look at the terms in the numerator, specifically the terms in front of the square root, we can factor out a 2. And those cancel each other out. The 2 that you factored out cancels with the 2 in the denominator. So you have -3 plus or minus the square root of 10. And we already knew that another 0 was x equals -5. So the zeros are x equals -5 and x equals -3 plus or minus square root of 10. Oh, we're the same. Now I haven't been doing this for the other polynomials for 2 reasons. 1, to save time, and 2, because I knew it wouldn't work. But one thing that sometimes can happen if a polynomial has 4 terms, like this one, is you can try to factor by grouping. Okay, so in this case it actually does work to factor by grouping. If you look at this first grouping, you can take out an x squared, and that leaves you with x plus 1. In the second grouping, you can factor out a 25, and that leaves you with x plus 1. So both of these terms here, this term and this term, have an x plus 1 as a common factor. So if you factor out the x plus 1 from both terms, you're left with x squared plus 25. Now, the reason that these are called zeros is it's because they're setting the equation equal to 0. If this times this is equal to 0, that means this factor has to equal 0 and this factor has to equal 0. This one's an easy one over here on the left, x equals -1. This one here, if you subtract the 25 over, you get x squared equals -25. If you square root both sides, then x is equal to plus or minus. And since you're taking the square root of a negative number, you have to use imaginary value. So this is plus or minus 5i. And those are the 3 zeros. X equals -1. X equals plus or minus 5i.
Okay, number 16. We need to make a degree 3 polynomial, but we've only been given 2 zeros, and that's a problem. The number of zeros is supposed to equal the number, or the degree, and it's purposely been done. You're supposed to remember the fact that 2 plus 3i has a matching pair 2 minus 3i. These types of zeros always come in pairs. They're called conjugate pairs. Next step is to form the factors from which these zeros came. So x equals 4. A good way to do this is to make each zero equation here equal to 0. So x minus 4 equals 0. That means one of your factors is x minus 4. If you subtract 2 and a 3i, you're going to have x minus 2 minus 3i. And then over here, if you subtract 2 and add 3i, you have x minus 2 plus 3i. So now you got to multiply all the parentheses together. It would be much easier to multiply the two parentheses together that contain the complex factors. So multiply here, you're going to have x squared minus 2x plus 3ix. Now multiply the negative 2, you have negative 2x plus 4, or minus 6i. And now multiply the negative 3i, and you're going to have negative 3ix plus 6i minus 9i squared. If you've done your math correctly, any term that has an I should cancel out with an opposite. So the negative and positive 6i, then negative 3ix, and positive 3ix, and even the 9i squared. It doesn't cancel, but remember I squared is really just negative 1. I squared equals negative 1. So if you have negative 9 multiplied by negative 1, that really changes into a positive 9. So every term now that had an I canceled. If you combine your like terms, you'd have x squared minus 4x plus 13 times x minus 4. And then multiply those together, you're going to have x to the third minus 4x squared plus 13x minus 4x squared plus 16x minus 52. Combine those like terms and you have your final product here. X to the third minus 8x squared plus 29x minus 52.
To the old problem here of finding the zeros. I know it might be a little bit overkill, but it's just an important skill to have, so I put it on here a couple times, more than a couple of times. It's just got to be something, if you want to be successful on this test, you've got to be able to find the zeros in the polynomial. So, P over Q plus or minus 1 plus or minus 11. So, let me try 1. And again, you want to make sure that you scan through the polynomial to check the missing terms. There aren't any. So, let's see. Doesn't look like it would be anywhere with that one. We're getting somewhere with that one. So we know that x equals negative 1, so x plus 1 is the factor. These are the coefficients of the reduced polynomial x to the third minus 11x squared plus x minus 11. But we've only found one zero because this is a degree 4 polynomial. There's a total of 4 zeros. We've only found one, so there are 3 more. Those 3 zeros are going to come from this factor right here. But we can use the same P over Q list. We've already said that x equals 1 doesn't work. I'm going to try that one again, so try 11. But synthetically dividing now on this reduced polynomial, so 1, negative 11, 1, negative 11. Let's see what we can get out of this. looks like we found another 0. So we already knew that x plus 1 was a factor. Now we know that x plus 11, or x minus 11 is a factor. And then these are the coefficients of the reduced polynomial x squared plus 1. Now remember, ultimately we're finding zeros because we're finding values that make this polynomial equal 0. So if this times this times this is equal to 0, that means that x would have to equal -1, x would have to equal 11. That also means that x squared plus 1 has to equal 0. If you subtract the 1, you get x squared equals -1. If you square root both sides, you get x equals plus or minus. The square root of -1, that's the definition of the imaginary unit I. So that counts as 2 zeros. These were the other two. X equals -1, x equals positive 1. Oh, sorry, positive 11. Okay, number 18 here. The values of p are the factors of the constant, so it's plus or minus 1, 2, 4, 8, and 16. The values of q in this case, since q is equal to 4, plus minus 1, 2, 4. So p divided by q, if we take the first value of p and divide it by all the values of q, we're going to get plus or minus 1. That's from 1 over 1. Then 1 over 2, plus minus 1 half. 1 over 4 is plus or minus 1/4. Now we move over to the next value of p right here, which is 2, and divide that by all the values of q. So we're going to get 2 over 1, which is 2. Then we're going to get 2 over 2, which is 1. We already have that one right here. We don't need it again. We're going to get 2 over 4, which is just 1/2. We already have that one. Okay, we move to the next value of p, which is 4. 4 divided by 1 is 4. 4 divided by 2 is 2. We already have that one there. And 4 divided by 4 is 1. We have that one right there. Okay, 8 divided by 1 is 8. 8 divided by 2 is just 4. And 8 divided by 4 is 2. So we have those. 16 divided by 1. 16. 16 over 2 we already have as 8, and 16 over 4 we already have as 4. So that's the list of possible rational zeros. We need to choose some from that list and synthetically divide. I'm going to skip right over to 2. I have a good feeling about 2. Alright, x equals 2 was indeed a 0, which means that x minus 2 is the factor. The reduced factor is 4x squared minus 4x plus 8. Turns out that this does not factor. So we use the quadratic formula. X equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. So 4 plus or minus the square root of 16 minus 4 times 4 times 8. I would recommend, rather than trying some mental math on some of these problems, that check it on a calculator. 16 minus 4 times 4 times 8, negative 112. And now 112 is 16 times 7. If we take the square root of 16 times 7, the 16 is going to come out as a 4. And then the minus sign is going to come out as an I. So this is 4 plus or minus 4i times the square root of 7 all over 8. Now if you look at the numerator, common factor there in the numerator is 4. And then 4 goes into 8 twice. So we've got 1 plus or minus I squares of 7 all over 2. So that counts as 2 zeros. Behind the zeros of x equals negative 2, so the zeros are x equals positive 2. X equals 2 and x equals 1 plus or minus I squares of 7 all over 2. Those are the 3 zeros. Okay, question 19. We need to find the volume of the box, but it says as a function of x. The volume of any box is equal to length times width times height, but this is not a function of x because there's 3 variables. What we need to do is describe the volume using only x variables. So when it's laid flat, the width of this box is 35 centimeters, but volume can't be found on a flat surface. You'd have to fold this into this box right here to find volume. So when you cut out these corners, to be able to fold it up, you're taking away length and width from the box, and you're taking x. So now the width is going to start from here and end here, and then the length of that is 35 minus the 2x values that you took out. And similarly here, rather than a length here of 24, you're going to have 24 minus 2x. So that's the length and the width. And the height of this box, once you fold it together, it says here that the height is x. So there's length times width times height. That's the volume of the box as a function of x. Now I know if you were looking at the answer key for number 19, they had the volume as something like 4x to the third plus something. That's just from multiplying this all out. I don't care whether you do that or not. You're fine to leave it in this form. Okay. The domain of V. This one you have to really think a little more logically rather than algebraically. Normally the domain of a function you find just by looking at the function itself and thinking, alright, what can or can't or shouldn't I plug in for x? And if we're just looking at the function here, you really could plug anything you wanted in for x. Negative values, positive values, fraction, decimals. The problem is this function represents a volume and x represents an actual length. And because of that, this is what's called a feasible domain or a possible domain. Since x represents measured distances, it wouldn't make sense to have x equal a negative value. You can't have a negative distance. So x has to be greater than 0 to make sure it's a positive number. But x can't get bigger than a specific value. For example, let's say that I were to claim that x equals 13. Now that's fine to plug into this function here. I can certainly do that. The problem is x equals 13 doesn't work in relation to our physical constraints of the box. Here's what I mean by that. If I say that this x right here equals 13, that means it has a length of 13. That also means this length has a length of 13, and that's not going to work because we only have 24 centimeters to work with. 13 and 13 would be 26. That's way too long. So the largest values that x could be would be 12 and 12, because that would add together to give you the 24 centimeters right here on that one side. So x can be no larger than 12. So x has to be some number between 0 and 12.
Okay. Question 20. This question actually comes from section 3.1, but it is applicable to chapter 3 in that it deals with polynomials. There's a key word here, 2 keywords, maximum, maximum, That's usually an indication that you're going to have to find the vertex of a parabola. So what we have here, we've got some river. We've got some rectangular pen here. And the perimeter of this rectangular pen is 2,400 square feet. But the question is asking for the area. The area of a rectangle is length times width. Problem is that's not a function. A function can only have one variable. So what we need to do is describe the area of this rectangle using only one variable. Now, since it's a rectangle, it's the same on the right and the left side in terms of length. So if I call this length x, that automatically means that this length is x. Now, we use the fact that there's 2,400 feet of fence remaining, or available to use. If we've already used 2x for the sides, that means for this bottom piece, there's 2,400 minus 2x feet of fence remaining. So what we can do is describe the area. Instead of length and width, we can describe the area in terms of x. And we can turn it into a function. And this is a function because it only has one variable, and it would pass a vertical line test. As it turns out, you don't need to graph this. It's not required in the problem, but as it turns out, it's a upside down parabola in terms of x and area. So if we can find the vertex, that's going to give us the maximum dimension, or the dimensions that's going to yield the maximum area. So vertex formula is the opposite of b divided by 2a, so negative 2,400 divided by 2 times negative 2. This is 2,400 divided by 4, which is 600. Now, 2,400 minus 2 times 600. 2 times 600 is 1,200. 24 minus 1,200 is 1,200. So the dimensions need to be 600 by 1,200. So those are going to be the dimensions right here. This answers the first part of the question. Find the dimensions of the pen that would yield the maximum area. And then what is the maximum area? Well, if we have those dimensions, the area is going to be 600 multiplied by 1,200, which is 780,000 square feet. Feet square. There we go. 780,000 square feet.